Hello everyone, I'd like to share a very simple proof of the famous Hardy inequality. But the Hardy inequality, there are probably many versions of Hardy inequality, but usually when we talk about the Hardy inequality, we refer this inequality. There are actually a integral version of Hardy inequality and this discrete version of Hardy inequality. Say we are given n number of non-negative real numbers. So here x1, x2, and all the way to xn, they are all greater or equal than 0. Well, we could have an infinite many of them. And then if we do, and then we need to revise the Hardy inequality into a infinite series, but that's fine. But we can start with a finite many of them. So we have all these non-negative real numbers. Then we have the stated inequality. We actually, if we want to explicitly write it out, we would have the inequality is the following: x1 squared plus x1 plus x2 divided by 2, which is the average of x1 and x2 squared. We add all the way to x1 to xn, the arithmetic average of them, and take square less than or equal to 4 times x1 squared plus up to xn squared. This inequality is hard in the sense that x1, x2, all the way to xn, they are not symmetric. So in a sense, if you cannot just replace x1 by x2, you cannot rotate them, and you cannot switch any one of them. So I think that is the hard part of this inequality. There are proofs of the inequality. You can check from different books, but I'm going to offer a new one which is straightforward and it's very intuitive. Now, let me offer my proof here. We notice that in order to prove this inequality, it's equivalent to prove the following version. So if we can find a1, a2, up to an, they are all positive real numbers. If we can prove that a1 times x1 squared plus all the way, we multiply x1 by a1, x2 by a2, xn by an. Then we take the inequality, we write it down, and we immediately notice that this is actually equivalent to the original Hardy inequality, because we simply multiply everything by a positive real number. So if the previous the original Hardy inequality is true, obviously this is true, and reversely, if this is true, then of course the Hardy inequality is true. But the benefit of writing the inequality in this way is we can actually choose a1, a2 all the way to an. Let's look at the general term from the left-hand side. The general term is a1 x1 plus up to ak xk divided by k and takes the square. But first, let's look at the square. By Cauchy inequality, we know this is bounded by a1 squared plus up to ak squared times x1 squared. We add it up to xk squared. And then we can divide it from both sides, k squared, and then the right-hand side, k squared. We do this to every term from the left-hand side. And then we immediately notice that the left-hand side is bounded by a1 squared x1 squared plus a1 squared plus a2 squared divided by 2 squared, then up to here is a1 square plus up to an square divided by n square. That's the x1 square coefficient. So these are the x1 square coefficient. What about the x2 square coefficient? That's a1 square plus a2 square divided by 2 square plus all the way to a1 square plus up to an square divided by n square. So that's the coefficient of x2 square. So, and then in the very end, we simply have a1 square plus an square divided by n square. That's the coefficient of xn square. That is the left-hand side. We need to add them all. And we want to prove this is actually bounded by 4 times a1 square x1 square, a2 square x2 square, up to an square xn square. So in order to prove this, now we just need to prove them coefficient by coefficient, which is we want to prove the x1 square coefficient. We have the corresponding inequality. We have the same inequality for x2 square, and then we prove the xn square. So consequently, we just need to prove the following. If we can find this a1 to all the way to an, so let's try. We want to prove a1 square. The xk square coefficient is a1 square plus up to ak square divided by k square. And then we keep adding this to the last one. A1 square plus an square divided by n square. We want to prove this is bounded by 4 times ak square. How can we find a1, a2 all the way to an so that we have this inequality to be true for a1 all the way to an? Well, we need to try it out. For example, we can try the following. So if we can somehow define a1 square plus all the way to ak square, we can let it to be, for example, k. And then this is equivalent to saying all a1 equals to a2 equals to ak equals to 1 for every k equals to 1 to all the way to n. So in a sense, if you want the summation of ai squared up to k equals to k for every k, then is necessary and sufficient condition is every a equals to 1. But if every a equals to 1, this will not give us our desired property, because we immediately notice that this will lead to harmonic series. And we know harmonic series, I mean the very first term, this will give us the harmonic series. And we know the harmonic series is not bounded. So this approach would fail. And therefore we can next check. We want a1 square, we add up to ak square. We let it to be square root of k. Because we want to avoid this divergent harmonic series problem, so we can try let a1 square plus all the way to ak square equals to square root of k. And this would imply that every ak is simply square root of k minus square root of k minus 1. For each k from 1, 2, and all the way to n. Now, let us check if we have the desired property. The desired property, which is right here, let's just check this. Now, the this inequality actually is equivalent to, we just need to check this one. Then we have the bottom is k squared. The numerator is square root k. And next one is square root k plus 1. And then we have k plus 1 squared. We add up all the way to square root of n divided by n squared. We want to show this is bounded by 4 times square root of k minus square root of k minus 1. Let us check this inequality. Now this inequality, how do we prove this? We notice that obviously we want to use integral. So we want to check a function. The function is just the x to the power 2/3. And this function we want to study. Where do we want to study from the integral from k minus 1/2 to infinity fx dx. The function is actually a decreasing function. It's like this, a decreasing function, and it's a convex function. So if we want to add up from k plus 1, we want to add it up, it's certainly bounded by the entire integral starting from k minus 1/2 due to its convexity. So here we use the convexity of this function. So in a sense, this is bounded by this integral. And how much is this integral? We can calculate. This integral is simply 2 divided by square root of k minus 1/2. So finally, let us check. If we have the desired inequality, 2 divided by square root of k minus 1/2 is less than k multiplied with, here, square root of k minus the square root of k minus 1 can be simplified as 4 over square root of k plus square root of k minus 1. So we just need to check this final inequality. Obviously, this is equivalent to square root of k plus square root of k minus 1 is less than or equal to 2 times square root of k minus 1/2. This time, let us check the square root function. The square root function is a concave function. And if this is k, if this is k minus 1, if this is k, the midpoint would be k minus 1/2 because it's a concave function. So by concavity, one of the Jensen inequalities, certainly this is true. And therefore, we finished our proof by choosing ak squared to be square root of k minus the square root of k minus 1. Actually, the inequality is not that hard to check. And therefore, we proved our version of Hardy inequality, which is equivalent to the original version of Hardy inequality. So I actually find this proof is much more straightforward and very intuitive. So I'd like to share with everyone. Thank you.